you need to read yourself. This is about conference dinner. Arrive at 7:15, and after you copy them down, I'll turn it off. Okay. So the first speaker of the morning is Fionn Murtagh of Royal Holloway of the University of London. So he'll talk on the ultrametric topology perspective on analysis of massive, very high-dimensional data stores.
Thank you very much. It's on, I think, is it? This thing? Can you hear me? Yeah. Okay. Makes no difference to me. I'd like to thank the organisers for inviting me here. I'm going to be dealing with a range of examples which discuss primarily the high-dimensional data analysis problem, clustering, for instance, in high dimensions. And some of the examples that I will show a little bit later are not particularly high-dimensional, but they are dealing with massive data sets. And the principles which I will be applying pretty much hold for all of the examples that I will be dealing with. One of the things that I want to basically convince you of is that one should consider the topology which one is using to analyze data as a very valuable tool to understand what's going on. You obviously know that in a metric context, a low-dimensional representation, for instance, there are particular properties which are associated with that. I am going to be dealing with ultrametricity as a sort of a guiding principle. Practically, we will see that that may be directly applicable. It may be in many, many cases, but at any rate, it's a sort of an overall concept to look at the data. Ultrametricity, if you wish, you can consider the hierarchical nature of data. Really, and I will return to this just in concluding, in many ways what I'm dealing with is having a type of symmetry principle which is at issue here, rather than sparsity, which I think is the principle applied to in quite a number of the presentations here. Just by way of a word or two on metric versus ultrametric, a metric satisfies a number of properties of reflexivity and such like, positive definiteness, but the important property really is the triangular inequality, which is as stated here. An ultrametric satisfies similar properties to a metric with the exception of a stronger triangular inequality, which is also referred to as the ultrametric inequality. And it's the set of relationships which are necessary when data is structured in a tree or hierarchy of the sort that you have here. So there's a little example of the ultrametric property. Now, ultrametricity can be forced on data. You can basically embed the data in a hierarchical, into a hierarchy. That's one thing, using a hierarchical clustering algorithm, for instance, in many shapes and forms, many types of those algorithms. Or in many cases, you can find a large extent of ultrametricity, in other words, innate hierarchical property in data. That I would show you in a few moments' time, and in particular, I would be looking at the simple structure of very high-dimensional spaces, which can be quite conveniently viewed in hierarchical terms. That, therefore, is the reason deep down why I want to have this issue of ultrametricity as opposed to a more standard metric embedding. Ultrametricity, all embracing, as we know, from various biological and lots of other contexts. Now, one of the things which I've looked into extensively over the past few years is how one assesses inherent hierarchical structure in data. If you carry out a hierarchical clustering algorithm on your data and look for the fit between your data and the hierarchy that you have just found, that's not a terribly good way to approach the problem. because the very fact of fitting the data is forcing it into a hierarchy. The question instead for me here, just right now, the question instead is, to what extent does any arbitrary data set have within it islands of hierarchical structure, or aspects of it, maybe not islands, but aspects of its overall, of all of the data that we're talking about. To what extent is there hierarchical structure in the data? And the way that I've approached that is something which some other authors have done in the past. In the physics literature in particular, there has been work done in this area, and also Israel Lehrman, who has published in 1981 an approach based on ranks. My approach is different, though. What I have done is to look at the triangles which can be formed between all triplets of points. You'll remember just from a moment ago the basic triangular inequality, which defines a metric space, versus the strong triangular inequality defining an ultrametric space. Well, there you have the mechanism to decide on whether on the extent to which you've got local or more awkward, let's say, global related properties of the data, which lead you to conclude that the data has considerable innate, inherent hierarchical structure. Fine. So therefore, this gives a mechanism, and I'll show you various examples in a short while where this is used to quantify the extent of ultrametricity. And I will further show you how that extent of ultrametricity increases impressively as dimensionality, as ambient dimensionality increases. Now, there is a problem, or a perceived problem, with high dimensional spaces. I'm going to now justify the claim that, in fact, high dimensional spaces, and the higher the dimensionality, the better. Then, in a certain sense, the simpler the structure becomes in high dimensions. And let me have a look at the work of a number of other people just to begin with, and basically also make the assertion that my work is really no different from what has been happening in the context of a number of areas, primarily statistics, but also the pattern recognition area and machine learning area also. The work of Hall, Maron, and Anne in particular relates to this. Some of the references are as shown here. I'm going to come back to them just in a moment, but actually I've skipped already just to the pattern recognition and machine learning area, another reference at the top here. And there is a considerable amount of literature which looks for nearest neighbor points. Where one looks for an approximate nearest neighbor, and one has a relationship like this. Now, the problem in practice is that the distinction between excuse me, candidates for nearest neighbors may well be linear. That is what one would hope. But in fact, in practice, it is generally, because one has to search areas and zones and so on of the space, it becomes a matter of the volumes between shells in the space. And that is bad news when it's a matter of the computational advantages to be gained by allowing the nearest neighbor to be an approximate one. So in this context, there is a situation, therefore, where it may well be the case that ratios of nearest to furthest neighbours actually tend towards being equal. In other words, there is no benefit at all in carrying out local search, because the locality of the search will actually embrace the full dimensional space. And that's what happens when you're dealing with a cost function, which is essentially volume-based and, sorry, having trouble controlling this thing, volume-based, and when the volume increases dramatically because of the increase in dimensionality of the ambient space. There's a similar point which is made in a nice little article by this person, Broyle, and the point made is, when is nearest neighbours meaningful, is basically to assert that as dimensionality increases drastically, then these methods basically have no justification. The approximations involved in carrying out nearest neighbours by allowing, closeness to the really best candidates, there is no gain when doing that. Just to return to the work of Hall, Marin, and Ahn, they have shown in the case of Gaussian data that a very simplified structure comes about when dimensionality increases. And this is nice from my point of view because it bears out examples that I will show you in a few moments' time. What essentially is happening here is relatively very easy to comprehend, because when you've got points in any space and let the dimensionality increase, what you basically have is that the points are mutually going further away, such that they become, they tend towards being equidistant as the dimensionality expands, as the balloon expands. So consequently, this is the sort of result, therefore, which is to be expected under those circumstances. In other words, as the dimensionality, which I'm representing by m here, increases drastically. And Dave Donohoe, and in this work, Tanner and Donohoe have looked also at this work. Again, I see this as very closely related to the perspective which I've developed. Not, in my case, I've not been particularly interested in Gaussian data, and I will explain a bit later using an example from the chemoinformatics domain, but also in some discussion right at the very end on the analysis of textual data. I will use those examples to explain why I am not particularly interested in Gaussian data. It's not particularly relevant in those application contexts. But okay, fine. I mean, there are examples here where, again, for Gaussian data, simple structures materialize in high-dimensional spaces. In other words, as the dimensionality increases, the points, as I say there, fly apart from each other as dimensionality increases. They do so in a way that relatively simple structures ensue, and furthermore, the situation I would propose in such a situation is not low dimensionality embedding, but rather finding the symmetries, or at least exploiting the symmetries in such a high-dimensional context. Now, so therefore, that was just a very brief review of literature which, to my mind, fully supports the perspective that I have. Now, if we have a high-dimensional simplex of the sort seen, I mean a convex hull type structure, or the tendentially simplified Gaussian, very simplified Gaussian structure that Hall and Marin have dealt with. Fine. Then the question sort of arises, or it's a pertinent question as to why one would bother with something like ultrametricity and so on. Well, there are really two reasons. First of all, there is a valid reason for saying that such spaces are also hierarchically structured, because of the fact that we have so many equilateral triangles in such high-dimensional spaces. Everything tends to be, all triplets of points, as you will see, as I will show from examples in a few moments, tend to be equilateral. That's one thing. Now, that's somewhat of a trivial case, however. But first of all, there are plenty of other examples, and I will show where inter-cluster relationships actually are related to the non-trivial aspects of ultrametricity. And there are other reasons anyway, I mean, as to why this is beneficial, like for instance that this is as good a structuring of the data as any in order to reveal the symmetry in the data. A hierarchical tree, after all, does encapsulate symmetries, the symmetries at each node, for instance. Fine. I'm going to look at a number of different examples. Really what I need to quantify the ultrametricity of the data and then to show that that increases drastically with dimensionality is that I need the scalar product which defines the angles in triangles. So therefore, I need the data to be in a scalar product space. And generally speaking, in these examples, I will assume that the data is Euclidean. And I will not rescale in any way, but I will be using the Euclidean distance because it's convenient. But this is essentially what I need for my mechanism for quantifying, the relative proportion of triangles which satisfy certain properties, and thereby the ultrametric or hierarchical content in the data. I might add, just as a remark, that if I had to go beyond that context, the immediate place I would look is in regard to what Lehrman did using ranks only to define exactly the same types of properties. Consequently, there is a direction that one can follow if that were to be too much of an issue in regard to the data that one is dealing with. But one other small remark, footnote, that I would just mention in regard to Euclidean is that if we're dealing with textual or qualitative, quantitative data, etc., correspondence analysis is an ideal method for producing a Euclidean embedding of the data. And that's what I would generally use for textual data. Anyway, okay, let's have a look at some examples of these. I'm going to show you just a number of different examples where, just for the moment anyway, I am dealing with simulations, and then I'm going to go on and look at somewhat more complicated cluster structures in the data. Here we have data generated in a unit cube. M, the dimensionality, that's allowed to increase. A small n number of points, that's just kept constant. Dimensionality, ambient dimensionality increases. The data are uniformly distributed in this particular case example. I'm going to show you some other examples just in a few minutes. And then I look at the triangles. Actually, because of just the computational reasons, I've looked at sampling of the triangles. But as I would show you in a few moments' time as well, these results are very stable in regard to this sampling. And then just look at the proportion among all the triangles that we're looking at, the proportion that are isosceles, strictly isosceles, the proportion that are equilateral. Both of those together allow for me to say that the data respects the ultrametric property. Therefore, the degree of inherent hierarchicalness, hierarchicity, if you wish, ultrametricity, in the data is measured by this. It's on a scale of 0 to 1. It's just a relative proportion. So it's just the relative proportion of ultrametrics respecting triangles relative to the total number of triangles considered, right? Just on a 0 to 1 scale. So consequently, as this approaches 1, we have essentially all triangles, nearly all triangles which respect the ultrametric property. Fine. So this just shows anyway, as ambient dimensionality increases, number of points very much irrelevant with regard to this, so long as we don't allow this to be really, very great, because if we do, then we just have to push the dimensionality much further. We've got to increase the dimensionality much more. That's the only difference here, but otherwise there is a lot of extensively these results are invariant relative to the number of data points that we're dealing with. So it's a low n. Let's say that in general terms, however, it's certainly the case that this is low n, large m or p, or whatever your variable is for the dimensionality problem that we're looking at, in this case, simulated data. And we see that the ultrametricity increases drastically. Same thing for hypercube vertices in terms of such simulated data. A very similar result. A Gaussian cloud, and this of course is consistent with the references, with these citations which I showed you in the last few minutes. Again, a very, very similar situation. So initially, having got to that stage of basically saying, great, as dimensionality increases, we have a very simple structure. The points fly apart. In terms, at least, of the equilateral triangles in the data, clearly, therefore, there is very simple structure in the data. But the question then arises, well, I mean, from the point of view of real life, we're not dealing with necessarily one single Gaussian cloud, but instead clusters and so on. So let's have a look, therefore, at what that means in regard to the clusters. Here we have, slightly overwritten here, we have ambient dimensionalities of 2,000 and 20,000, and we have a set of points, in both cases, 3 sets of 100 points each, with mean 0 for all values and variances for the Gaussian clouds, and we have a situation where you have a tightening of the histogram of distances, pairwise distances. And that is going from the lower dimensionality here to the higher dimensionality. Now I'm going to look a little bit in more depth at just what that is. And I'm going to step back to the case of 2 Gaussian clouds with these characteristics. So they are pretty well separated, and what you see, therefore, is depending on the ambient dimensionality, is quite a remarkable difference in this situation. You've got 100 points in one cloud, you've got 100 points in another cloud. The ambient dimensionality for both is 20. The ambient dimensionality down here is 20,000. And you have in the histogram peaks, you have the internal. Let me just see here. We have the within pairwise distances in this peak, and we have the intra pairwise distances, the between cluster pairwise distances, which are larger because these clusters are well separated over here. So we just therefore have a situation where the tightening is increased. Then the results from the point of view of quantifying the extent of inherent hierarchical structure in the data, just as before, is shown in this progression, and we get something which approaches essentially complete ultrametricity, near enough to it. And again here, just to give an idea of the stability of the results, here are a number of different results for that case of the high dimensionality. When we have a situation of overlapping clusters, obviously the outcome is more messy. And that is what I want to look at now, because I want to go and use this for clustering, for finding clusters in very high dimensional spaces. So consequently, we have a situation with here where the simulated data has the characteristics shown, the same values of mean and standard deviation on each of the dimensions, but we have a few different clouds in the overall context of the data. And here you see that, again, we have this increase in ultrametricity, but not quite as impressive before. Why? Because simply the clusters are overlapping. Consequently, we've got less of the flying apart type of view of things compared to what we did before. Flying apart, I should add, relative to other pairwise distances. In the context of that data that we've just seen, therefore, just one of the dimensions, notwithstanding the fact that the data might be of high dimensionality, just one of the dimensions, we have a projection of this sort, and we have, in fact, 4 Gaussians in terms of the generation of the data. So you can see that the situation is not terribly clear-cut. If, however, we look at the pairwise distances, and again look at the histogram of the pairwise distances, we do see a much more readily exploitable situation. To begin with, therefore, on the top, we have, we can perhaps pick out the Gaussians, the properties which are related to the original Gaussian clouds that constitute our data. In the bottom, however, we've got an even better handle on how we might approach the problem of finding the clusters in the data. Remember that we're dealing with distances here, and we've got to go back, therefore, from these distances to the original data. So what we want, therefore, to find is that in some of the peaks of this histogram, we want to find a peak which relates to the internal pairwise distances from one particular cloud in the overall data. Then we want another peak, let's say, to be associated with the pairwise linkages, the pairwise distances between two of the clusters that we're dealing with. The problem, however, is that we may find multiple cases which are mapped onto one of the histogram peaks. That's the problem of disentangling this information in order to allow ourselves the possibility to use it to say that this corresponds to, let's say, clusters A and B, it's the inter-pair distances, and from that we can therefore, using that and using, let's say that this is the internal situation for the first of those clusters, etc. We could use that information to go back to our data, but you can see that we may have some limits in how much we can do that. So the question, therefore, becomes that of cluster identifiability. And we can go so far with this, and let's just have a quick look at just how far we can perhaps go. Here I'm going to use an example which is as follows. At least look at the, I'm going to actually, look first of all at Gaussians, means here, well separated. Consequently, we would expect in that case, and we find it, 3 intra-cluster distant peaks, 3 inter-cluster distance peaks. We find that all the more so as the ambient dimensionality increases. Now, let's add another cluster and find a situation where we have here 4 clusters. So we have a cluster of these characteristics. Remember again, mean standard deviation, the same for convenience on all dimensions. It's a simplification, but it's at least something which allows the data to be generated very, very straightforwardly from this. So therefore, 2 clusters here of those properties, another 2 clusters of those properties, another 2 clusters of those properties, and finally a bigger one of just that property for the last cluster. And we're dealing with equally sized subclusters, so let's just have a look at how many data points have I got here? Don't quite remember, but it was, I think it was 300 points and divided into these clusters. In any case, from these clusters, and using the reasoning as I've just shown you, we can have up to 28 peaks in the histogram of distances because of the inter and intra relationships here. Now, this is what we find. Okay, it was 90 points actually, which in total, and that's the 3 cluster case which preceded in terms of the example just shown. And now here is the 4 cluster case, 120 points. And again, tightening of the histograms. And as I said to you, 28 peaks we can have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 there. Why? Because of the a number of the clusters in terms of pairwise distances within them getting mapped into the same histogram peak, or the between cluster case again mapped onto the same cluster peak. Consequently, this limits how far we can go in terms of the data. I think this was the one actually which is related to the final data definition seen just a moment ago. And you can see here, let me just see, 1, 2, 3, 4, 5, 6, 7, 8. There are 14 at least clearly distinguishable peaks here, but just in that count, I've not taken that as 2, but rather as 1, and so on. So you can see that falls short of the 28. Again, this is the identifiability problem that I've mentioned. We can have, because of the closeness of the clusters, or even more so, the fact that they may be overlapping, then we will not find a clean situation here. But we do find, however, that we have considerably greater possibilities as we increase in dimensionality. Preliminary conclusions. Well, scalar product, at least used by me in terms of the angles which are at issue in the triangles. I've been looking, though, beyond that at the distances, pairwise distances, and there's a little example there of the Fisher iris data where a very impressive result can be shown here. Now, let's have a look at how this might be used to associate it or to tie it in with model-based clustering. And I want to use the model-based clustering for tackling the problem of identifiability, which I've essentially raised over in the last few slides. And let me have a look at first of all, some simulated data, and then I'm going to move on and look at a more problematic case of financial data. But here I'm going to look at two signals which have been generated to have mildly long-tailed distributions. I'm going to stick them end to end, and I'm going to look for my ability to distinguish them. And this could be indicative of Forex type financial data, or vibration measurements in a mechanical engineering context. This is the first data set which is used. This is the second data set, and then end to end we have them here. And I'm going to take windows on this data in order to have, therefore, points in a space defined as we allow these windows to slide along this data. And what I want is that the points which I have in that way in a space of ambient dimensionality given by the window length, I want that to allow me to be able to say something about the dividing line between the first data set, which is this part here, and the second data set. Actually, the data sets are as shown here in terms just of an example of what the data is like. The data sets are 2000 of that class and 2000 of that class. So I want, therefore, through a time series embedding, I want to have a look at the data. Example of the first signal, example of the second signal. Now, what I am doing is, as before, let's have a look just at what dimensionality means. In other words, window size on the data. If I allow the data, since I can generate any amount of data that I want here, allow the data to go to 200,000 in terms of dimensionality. Situation is not quite entirely clear-cut because we do not approach total ultrametricity, but from the results before, if I could go much, much higher, then I would approach even higher values of ultrametricity. Fine. This is only part of really what I'm interested in here. But here is what is of much greater benefit. It's a nice example of the data, what we find. We find basically that the internal pairwise distances. Now I'm dealing with distances here, as opposed, let's say, just to the angles which I was using on the last slide for quantifying the extent of ultrametricity in the data. But this is what I want to make use of for the cluster identifiability, which is the task I'm addressing right now. Here we have internally within cluster 1, internally within cluster 2, and between the clusters we have these. What we're dealing with are distances. What are the distances between? They are between the points extracted from the data. What are the points? They are simply the vector associated with a sliding window on the data. So I have therefore taken windows of the data, used those as points in a space of high dimensionality. In this case, the dimensionality is 200,000. In other words, the window length is 200,000. So you see anyway here that this affords us a very immediately useful way to demarcate what is associated with cluster 1 and with cluster 2, and then allows us to go back to the original data. Let's have a look at a real case where I do go back to the original data. Let me just see, this is by way of summarization. There is no normalization applied here. I don't want to rescale in any sense. I just want, however, to look at the distances in order for the clustering task. And I find that the greater the dimensionality, that's excellent. That's what I want, because that helps a lot. Let me just see in regard to this, just to note one thing, because I'm going to show you now the use of further analysis of the histograms of distances, and I'm going to be using model-based clustering on the histogram of distances. So in a sense, it's interesting to note that there are aspects of this work which is both model-based and distance-based, and traditionally, there has been sort of a distinction between these approaches. Either you took a distance-based approach and you advanced in the direction of agglomerative hierarchical clustering, for instance, where you used dissimilarities or distances or whatever, and that was the essential tool that you used to construct your hierarchy, or you used some sort of model-based approach, for instance, using a Gaussian mixture model for the data where you wanted to bypass distances and so on. In a certain sense, I'm using both. And I think that's quite an interesting aspect. It's basically a synthesis in a way of the two approaches. But I'm using them sort of in a way which is not detrimental. I'm not dependent on the distances as such. In fact, I'm using an approach which is as simple as possible in regards to what my needs are as regards those distances. And as you will see in a moment, well, there's flexibility here too. Now, I took data, financial futures data, which is from a company based in Oxford. And I looked at one particular commodity symbol in that, getting 95,000 values. And the data looked like this. And I want to segment that data in terms of essentially the variability properties of that. I want to segment it into successive segments and in order to characterize that signal in terms of different regimes. And therefore, the situation is very analogous to the simulated mildly long-tailed two-class situation that I showed you just a few moments ago. So, with this data, let me just show you the kind of things that I did to play around with it and to see, first of all, how I could benefit from high dimensionality, then how I could address the histogram of distances, which is much more messy in this case compared to what I have shown you, and then how I could go back to the original data, at least in this case, in order to segment the signal. So I've looked again at windows on the data. given that there are about 95,000, just over 95,000 values, I just took some simplifications in terms of going so far with the data, and I wanted to set this up just programming wise in such a way that it was convenient to do so. So I just basically set the starting point for the windows as being the same in all cases, but the window lengths, hence the embedding dimension, those values were allowed to increase. And note that with the high dimensionality case, the high embedding dimensionality case, or the long window length case, there is a lot of overlap in the data. That I don't mind. It will confuse the situation, the context, but as I will show you, I'm still able to do something with the data. So, fine. So this is therefore what we find. And this is, as I've said to you just now, a much more messy situation compared to what we've looked at on the simulated data. We have now, I've gone to a dimensionality of 10,000. It wasn't, well, with 95,000 or whatever values in the data, I did not want to go a great deal further because as it's clear, sliding windows on the data, if they're of length greater than 10,000, well, you're going to get everything just overlapping. Therefore, that was as far as I could feasibly go, but that's the histogram of distances which I found much more messy compared to before. Not in any case, not in any sense clearly distinguished like in the with the simulated data sets. So I still want to do something with that. Just because of the sliding windows, the numbers of points used were in the three different cases were more or less the same, but the windows sort of went over the edge, so to speak. Consequently, there were somewhat fewer points. That's the value of n that I'm using, okay? And dimensionality, value of m in my terminology, are these values, and these are pairwise distances, so therefore n times n minus 1 over 2 in total, from these n values. So fine, I want to still do something with this, so what do I do? I know in my heart and soul that as dimensionality increases, I'm expecting to find clearly distinguished peaks. Let me assume, therefore, that the peaks are there, confused, but they are there. So let me therefore use a Gaussian mixture model on this data and see what that brings, and see then if I can find a good solution. And what I find is, let me just step back in a moment, I'm using BIC as an approximation to the Bayes factor for the number of Gaussians in a Gaussian mixture model, and I look at the data and find very clear evidence for a 5 Gaussian fit to the data. So in other words, therefore, I find a best solution of 5 Gaussians with these properties. Let me quickly step back again before using this. So I have fit the Gaussians to this data, and that is what I'm doing, trying to find evidence for the clusters on the basis of those histograms. Now, for 5 clusters, if those clusters are really very well distinguished, then I will be able to find them. I've got to, manage to do that in some way. So what do I do? Well, here's the kind of quick fix, if you like. I actually took the data used in the high dimensional space, and I used a hierarchical clustering purely to find the 5 clusters which the Gaussian mixture modeling gave me. Don't forget that the Gaussian mixture modeling was on the basis of the histogram of distances. So I want to just to find that, and I was assuming again that that histogram of distances essentially related to the peaks relating to individual clusters. There may be some, assumptions involved there. Obviously, one could look at alternative possibilities. However, the approach adopted is frankly quite reasonable. So I want just a quick fix to find 5 clearly enough distinguishable clusters, and that is what I used to do that. And then from that, knowing what the clusters were, I went back to the original data, and 2 of the segments here in the original data are both associated with one cluster, so you have 6 regions in total in the data here. So therefore, that allowed me to go back to the data from the processing of the histogram. You will see there, therefore, that in this case we have a typical messy real-life case, but I still use the same approach, which served me well, very well, in fact, with the simulations beforehand. Just as a matter of interest, and again, a small point, that low dimensionality embeddings of very simple structures, as we find in high dimensional spaces, ought to be extremely simple if only we can find them. And this is a principal coordinates or metric multidimensional scaling map in 2 dimensions of the pairwise distances, and they are in sequence along the curve which you see here. And I would suggest that it's not at all unusual to find very, very simple low dimensionality embeddings of the simple structure in high dimensional spaces, but as I said, subject to having subject to really, being able to focus in on it. It's not easy to know beforehand if it will be linear or non-linear, curved, as you see here, probably open to a very simple expression or not. Okay. Now, what I'd like just to quickly deal with in a few minutes is how one can adopt other approaches which are also related to my essential starting point of the fact that there is often a lot of hierarchical structure in data. What sort of other hierarchical structure may be of interest in data, and how can one also benefit from that? And I'm going to look at it primarily with the goal now of computationally efficient clustering algorithms. I'm going to use an example of data from chemoinformatics where matching is needed between molecules of the sort that you have here. There are mainly 3 ways that this is done in practice. One way is using coding schemes as illustrated in this example. A second way is using 3-dimensional structures of the molecules. And again, maybe a coding scheme, but at any rate using 3-dimensional properties. And a third way is using even more simple molecular and other molecular density and other more simple properties, much even more simple than you see here in regard to a coding scheme, or let's say a data collection scheme. So fixed length descriptors, and I am using just over 1 million chemicals. They are just in terms of these coding attributes, just over 1,000 attributes, they are approximately Gaussian, but in real life one is often dealing with other types of distributions. This is the other projection, the other marginal of the matrix, which crosses the chemical compounds with the descriptors used. And those descriptors are long-tailed and have the properties as shown here. Now, what I want to do is, as said, I want to develop an approach which is more efficient, computationally efficient. And I'm going to have a look, just assume for one moment that we have real valued data and that we only have one coordinate, one value on the data. Now, one can look at the precision of the data. From let's say, a Euclidean point of view, if one looks at restricting distance to be limited, to be a function of the precision of the number of decimal points in the real value data, then that's an approximation. But it's not an approximation necessarily from the point of view of another metric, as for example, the one shown here. The one shown here is used in some areas of topology. For instance, it is associated with the Baire space, and it is used in dealing with strings, where we have the so-called greatest common prefix metric, which is furthermore an ultrametric. It is in fact an ultrametric which is bounded from above by 1. And I'm going to use that metric. One reason the main reason for using it is to allow for computational efficiency. Here you have an example, a real valued, just one value. Another value, precision is 3 in total, because of 3 decimal points, nothing more than that. I'm assuming that for convenience I can always have my data as being bounded from above by 1 if I wish, and bounded from below by 0. I can arrange that. So I'm assuming that that's the case. And then in that case, the distance between them is given by this value. And because the third value is where they first differ, and consequently you have that as the exponent. Fine. This therefore is an ultrametric, but therefore it inherently, immediately and directly gives you a tree structure between the data attributes, the xk's and the yks that you're dealing with. The limitation perhaps is that you have just one value for your data for the moment. And I'm going to use that on the chemical data. The one reason immediately why I had real values is that I normalized the data in order to account for that power law type marginal. And that's standard practice in, for instance, the information retrieval context, where such normalization is referred to as inverse term frequency mapping, ITF. And it's therefore okay. So therefore, that resulted in real values. But from the point of view of the 1025 dimensional space, let me just see here. I looked at just one final thing. We looked at random projections in regard to the data in order to give just one dimension in this case, and some properties of the distance are shown here. But more perhaps of relevance is a comparison of this, of carrying out clustering based on this, what we've termed a Baire distance, the Baire metric or ultrametric, giving directly a hierarchy on the data, comparing it to k-means, and reasonable results can be found, but admittedly this is very dependent on the particular data. Good. That's just basically an example of the use of this of an approach which seeks to well, in this case, to embed the data in a hierarchy in order to ultimately here, ultimately the objective was to facilitate nearest neighbor search, best match searching among these chemical compounds for for lots of different reasons, like, for instance, merging databases or specifying intellectual property by checking whether some particular compounds have been looked at before. A situation where this ought to pay even better dividends in terms of immediate usefulness is where the n that we're dealing with, the number of objects, is vast, and where the dimensionality may be relatively quite low in order to allow for the random projection that was used. And one example of where that might, where that can be expected to work very, very well is in astronomy data. because even if one is dealing with a feature space, an attribute space, in astronomy, typically the number of dimensions is not that large. It may be a dozen or 2 dozen or whatever. Generally it's not large. And furthermore, if one is actually dealing with cases where astrometry, let's say, is the issue and you've got to match astronomical catalogues, then you are dealing with 3 dimensions. The X and Y, which are right ascension and declination, and the third dimension, which is redshift. So it's not a difficult problem. The other problems which do arise, of course, is that the data is nothing to do with being Euclidean. That's a different matter. But at any rate, that just points to the fact that the clustering based on the principle of just described, where the precision of the data is at issue, in order to derive a hierarchy from the data very directly from the initial data, that ought to be far more suitable than any alternative based on, for instance, the Euclidean distance. So just 2 things by way of conclusions. First of all, just a general set of remarks. High dimensional spaces are very different. That was the major part of my talk. The simplified and ultimately very simple structures which result are of immediate, they offer immediate possibilities for exploitation. And just by way of where I think we see the benefits of this work in terms of the future, and where it may could be considered as resulting in qualitative difference relative to the way the things have been done up to now. Pedro Contreras, who is in the audience here, is working on large archived data stores which are provided as a service to business. Email in particular may well, for legal compliance reasons, need to be stored for a certain period of time. There may therefore need to be searches carried out in such very large email collections, and consequently you've got text data which must be searched through. The type of approach outlined for the chemical data is ideal in that context. And those data set sizes may well be petabyte sized, and consequently computational efficiency is a very high ranked objective in such data. Furthermore, the data may be compressed, which in fact could be beneficial, because compression very often is based on finding correlations in the data, consequently finding clustering in the data. That may well be very advantageous in terms of facilitating retrieval. The other area which I'm very interested in pursuing is also using essentially text, not necessarily always text, but mixed text and numeric data, because hierarchy expresses very well the notion of innovation, novelty, anomaly. You can consider, for instance, data observations which are clustered together, and some other one which is quite novel relative to those. It's immediate almost to represent that as an extra node in a tree. So consequently, although information retrieval in context has been proposed as a slogan almost to focus work, I frankly think that information retrieval out of context is more interesting. And the application domain, because of my current work with Science Foundation Ireland, which I'm interested in applying this to, is to analyse the situation when you have, for instance, a funding proposal, a funding program with, let's say, a number of hundred, let's say 700, as was the case recently, 700 proposals submitted in the context of a particular funding program, to look at the interrelationships between those data sets. Number one, to look for overlap and redundancy, to look for clustering, to look at the evaluation panels and the work of those in terms of consistency of process, and to look also at the relationship between that data, let's say 700 funding proposals which come into you, versus in relation to the wide domain of the evolution of the disciplines which are related to that, therefore pulling in data from outside. I mean, that's a massive problem, but one where innovation is what is essentially targeted, and consequently where the inherent hierarchical properties of the data are there to express that innovation. And therefore, that's just an example of work which I have very much in mind currently, and which is incredibly ambitious and also requiring vast amounts of data to, as part and parcel of that data. Good, thanks. Thank you.
We have probably 2 minutes or so for a few quick questions.
I've never heard any of this before, but I'm trying to put what you did in context of what we've heard before in this conference. And it seems for the problems we've heard about like yesterday, this would be just the wrong way to go. Let me give you an example. In your first examples, it seemed to me, I may be wrong, that you're basically just using the central limit theorem. Each coordinate is independent, and you get more and more of them in higher dimensions. So of course, we know that a statistic's going to get sharper and sharper. But we were interested yesterday in sparsity, where we thought maybe one coordinate was detectable, and all the others in the different clusters were exactly the same. 99% of the features were useless. There was one feature that was useful. If you combine equally all the information from the 100 features, we saw you couldn't see it. That was what the point of Fionn's talk was yesterday. And that, in fact, if you have that prior, you better look pre-screen and look one at a time. So it seems like this is something, to me, where you have a specific, like most things with high dimensions, you can find things if you have the right prior and have the right method for what you believe. But there's no universal thing, and this would do terribly with yesterday's problem.
I've had this discussion before, and the person I was discussing it with was basically proposing variable selection, and I see that as being close to what you've said, and at any rate, embedding in some small dimension which will facilitate the kind of things that you're doing. I mean, basically, is what you've said. And I agree with you that in some cases you're right. You're totally right. But I would also say that you are not right when it comes to a lot of other areas. Just as one example, when dealing with text and the text terms are what characterize your documents or other texts. Of course, there are situations where very particular terms might represent the data best, and consequently it goes in your direction. But in general terms, no. In general terms, the entirety of those descriptors are needed. Frankly, in the chemoinformatics case, there too, the attributes, whatever about purely from the algorithmic point of view in terms of random projections, but otherwise, I mean, all of those attributes are potentially valuable. And from the point of view, therefore, of data interpretation, in a certain sense, you've got to keep them all under consideration. I really do think that there are many situations where all dimensions are needed.
I don't disagree. I'm just saying not all situations.
Pardon?
I completely agree. I'm just saying not all situations. You have to have you have to decide what situation you're in.
Yeah. Fine. I mean, absolutely. That's why, though, too, I did indicate that there are particular problems which drive me, and where I am not prepared to let go of attributes or features or whatever, right? So, these problems are important ones in their own right. So, there's a possibility for both. both perspectives.
Just to augment, Jim Robin's point, that in the simulated example that you have shown us is really a clear law of large numbers as dimension increases. So it's and then later on when you apply to the real data, you says there's no clear distinction in terms of the peaks and so on. So my curiosity is the extent to which such kind of feature, clear separation in distance, we see. In all your simulation cases, it's clearly mathematically proved that by law of large number it won't be like that. So the question is how general that kind of distinguish clustering you can distinguish space or other kind of examples.
Well, I think we'll have to wait and see how that works out. 95,000 or so, values in the financial signal. In principle, that could be far, far greater. Textual processing, typically sort of the order of 10,000. Maybe not terribly high in terms of dimensionality, but nonetheless, it may still be very, very beneficial. My essential point, right at the start, was that one can look for sparsity in the data, and I did, after all, show in the financial case where there is incredible sparsity, right? So consequently, I do not view this as saying that sparsity is wrong. By no means. In fact, I made the other point, that basically the opposite point, basically that sparsity will be found when structure is simple, consequently when the dimensionality is high. But I also made a point that symmetry is a very important principle in terms of data interpretation. And the symmetry which is provided by the hierarchical structure is a valuable way. It's multifaceted, it's sophisticated, and so on. And that is also a very important principle. And there are areas where this type of work is needed.
Yeah, so since we are out of time, let's move on. I'm pretty sure that people have questions, but during the tea break, you could ask Fionn again. So let's thank speaker again.